Hello, everyone. I'm giving a talk today, a short talk about tritium. Um, and I hope to show you why we should really be better versed and have more information about tritium. Okay, next slide, please, Mary. So the first thing is, well, what is tritium? Tritium is the radioactive isotope of hydrogen, H3. It's the lightest element there is, and that causes a lot of its unusual properties. But going on here, um, it's radioactive. It's got a half-life of 12.3 years, which is quite long, and relatively speaking. It's a beta emitter, a pure beta emitter, with an average energy of the beta particle, which comes off of 5.7 keV. It's got a maximum of about 18, but we should really stick to the 5.7 average. Now, the point is that because it's got a very low, shall I say, very amount of energy, it means that tritium is not an external hazard, it's an internal hazard. It's got a low range in cells of only about 0.6 microns. That's millionths of a meter. And that's about the same diameter as a human chromosome. So wherever tritium is, you've got danger zone. And of course, that's the whole body, effectively speaking. Okay, next slide. How do we normally see tritium or experience tritium? Well, its most common form is tritiated water, or water vapor for that matter. And if it's water vapor, that means it's an odorless, invisible gas, which means it's very difficult to monitor and to be aware of. Now, the problem is that ordinary water is H2O, of course. And in tritiated water, one of the two H atoms is replaced with a tritium atom to get H2O. Another form of tritium is elemental tritium gas, HT for short. Next slide. Now, this is a diagram of a water molecule. You got an oxygen atom and separated by two hydrogen atoms at an angle of 104 degrees. Now, the thing about tritiated water is that one of those H's, sometimes both, but mainly one of them, is replaced with tritium. So basically, you've got not something in the water that's tritiated, but the water itself is tritiated. The water is radioactive. Next slide. So is radioactive water dangerous? Well, yes, it is. Obvious question, perhaps, but the point is that we, as humans, are, well, we're just bags of water. 66% of our, on average, of us is by weight is water. And that means that our bodies avidly take up water, whether it's by breathing it in, whether it's by ingestion, whether it's by skin absorption. And here's the killer punch. Our body can't distinguish ordinary water from tritiated water, from H2O. So it gets into our bodies, lickety split really fast, and we're not even aware of it. Next slide. Why is tritium so important? Well, tritium is produced in all nuclear reactor plants in very large amounts. By how much? Well, for a light water reactor, say a PWR, we're talking about a trillion becquerels per year. That's a million becquerels per year. And found in both nuclear fuel and coolant water. And the thing is that tritium is both an activation product and a tertiary fission product. In other words, it's formed inside the nuclear reactor, both by activation of ordinary hydrogen and as a tertiary fission product. When you have the splitting of the uranium atom, out comes a tritium atom as well. Okay, next slide. How do we get it? Well, as I mentioned earlier, by inhalation, ingestion, or skin absorption. Next slide. Now, the thing about tritium is that it's got a whole range of unusual properties, like no other radionuclide. Just going through them very quickly, it's got an extremely high mobility. It's water, let's face it. It's not that it's soluble. It is the thing that makes other things soluble. It's a solute, or I should say it's a solvent. We have also the fact that tritium has high exchangeability with other hydrogen atoms, and it's got this ability to bind with organic materials to form OBT, which is organically bound tritium. That means that once it gets inside us, it sticks inside us and stays for long periods of time. Now, tritium, as I mentioned earlier, has got a very short range beta particle. So its damage depends on the exact location in the cell. And if it happens to be next door to DNA, then you have damage to the DNA. In other words, it's serious. Tritium is often described by those who don't really know, particularly in the nuclear industry, as a weak emitter, but that's not true. The point is that in radiation biology, nuclides which are weak are 2 to 3 times more dangerous than strong emitters. I'll repeat that. So-called weak emitters are, in fact, radiologically speaking, 2 to 3 times more dangerous, more hazardous than strong emitters. But the problem is that when we come to look at radiation protection, almost no recognition is given to tritium's ability to incorporate in organic molecules and stay there. None whatsoever. So the end result is that when you look at tritium, dose models for tritium, they significantly underestimate tritium's doses and its consequent risks. In other words, the models used for tritium aren't worth the paper they're written on. So we have to look at it very carefully indeed whenever we see tritium being released or involved. Okay, next slide. These are a number of reports, and there's half a dozen here, 5, which go into tritium in quite a lot of detail. The most important one is the first one. AGIR stands for Advisory Group on Ionizing Radiation. That's a group which reported to the HPA, the Health Protection Agency in the United Kingdom, back in 2007. It published a report, a booklet called Review of Risks from Tritium. Went into quite a lot of detail and basically blew the whistle on tritium and said, look, we're going to have to recognize that the relative biological effectiveness of tritium is at least 2, maybe 3 times more dangerous than the standard referent radiation, i.e. A 230 kbp X-ray, mid-range X-ray. But there are a number of other reports. Look at Melantescu, Galliero, and Tekia. They're all from IAEA. There's my own report, which looks at the RBE and weighting factors for Auger emitters, which are kind of like tritium, and low-range beta emitters with particular reference to tritium. That's an 11-page report, which I wrote and was published by a journal which normally doesn't publish, how would I put it, reports critical of radiation, but it did in this case. There's also a report by Arjun Makhijani and Mike Thorne in 2006, which had, the report was called Signs for the Vulnerable, Setting Radiation and Exposure Health Standards to Protect Those at Risk. And one chapter is on tritium, chapter 7, very good chapter. And finally, in 2014, 8 years ago, I published a hypothesis to explain childhood cancers near nuclear power plants. And that basically involved tritium. Okay, next slide. I've put this slide in because at previous talks, we've talked about the dangers of used nuclear fuel. And I found this slide which shows you the number of tons of heavy metal, which is basically uranium, in pools, wet pools, and in dry stores throughout the world. You can see that the United States has got the largest figure, 90,000 tons of heavy metal. By the way, a ton or tonne is 1,000 kilograms, okay? That's what the definition of a tonne is. But you can see Canada has got a lot of used nuclear fuel. So does France, Russia, Japan, Germany, Sweden, and United Kingdom. If you add them all up, you get 250,000 tons of heavy metal in terms of spent nuclear fuel around the world. That's a serious problem. And I put it in here because it's a useful piece of information. Next slide. Now, one problem I want to mention is that people think that once you close down a nuclear reactor, and you're taking the fuel out, that's the end of the problem. Nope, nothing could be further from the truth. This is a fact which is not widely known, so heads up here. The fact is that high levels of radionuclide emissions are released from shut down reactors. Which radionuclides? Tritium and carbon-14, mostly tritium, in fact. If we look at UK emissions data, just for the sense that I'm aware of this, it shows that reactors which were closed, almost 30 years ago, are still emitting large amounts, 2 terabecquerels a year of tritium. And in 2016, that was more than 20 years later. By the way, the fuel has already been taken out of these reactors, right? So what is going on here? Why are these reactors still putting out tritium and carbon-14? By the way, it's not just the UK. Similar patterns are not just at Windford, but at Trosveneth, Dunray, Chapplecross, and all closed Magnox, and these old-fashioned reactors in the UK, which are now closed. And it's not just Britain, it's Canada too. The small reactors at Whiteshell and Ralston, closed more than 30 years ago, with the fuel taken out, are still emitting 10 to the 9th gigabarrel quantities of tritium. These are small reactors, by the way. So that's why there's a relatively smaller amount, but it's still 1 billion becquerels a year. So what's going on here? Next slide. Mary, could you go back to the previous slide, please? I better explain why. It's no good just me saying this is occurring, but I better explain why. It's this. The tritium comes from the concrete structures of the reactor and the containment vessel. I'll repeat that. The tritium is contained and is released from the concrete structures of the reactor vessel and also the containment vessel. Why? Well, you see, these are old reactors. They've been operating for what, 30, 40 years or so. And during that time, the water or the hydrogen atoms in the concrete has become activated by the neutron bombardment from the operation of the reactors. I'll repeat that. The water molecules in concrete, and there's a lot of water molecules in concrete, have become activated by the neutron bombardment over the 30 to 40 years lifetimes of these reactors. And when you close the reactor down, what happens is that tritium oozes out of the concrete and you get very high emissions. So closed down reactors, even with the fuel out, are still dangerous. Okay, I think that's it. The next slide. Yeah, that's. I'll leave it. There may be questions here. On my website, I have a page devoted to the hazards of tritium, which people can look at their own ease. But if there are any specific questions, I'll do my best to try and answer them. Okay, thanks very much for now. Bye.